All right. Okay, one last announcement. People on Zoom, I will almost certainly not be able to check the Zoom chat very frequently. And so if people on Zoom, if you have a question, I think the best way would just be to unmute and just call out into the room. Other than that, if other people inside the room have questions, then you just feel free to raise your hand and I'll try to get to as many as possible. I can't promise I'll answer everything like during exactly the review session proper, because just so that there's enough time to cover all the things that are on the exam. But of course, if you have questions, I can always like answer them right after the review session. All right. Any other questions before we get started? All right, let's go ahead and get started. So the idea for today's review session is I'm going to present everything in approximately 2 parts. And the 2 parts, the first part is going to be essentially a very fast tour of all of the mathematical structures that we have been dealing with. That starts with propositional logic, set theory, functions, relations, and automata. I'm going to, so I hope that section will be a little shorter than the second part, which will be on probability, statistics, and combinatorics. I've chosen the topics to go over specifically from the practice exam. So I've looked at the practice exam, figured out exactly what are the techniques that you will need to know, and basically structured the topics for the review session accordingly. So the first part, I'm going to put particular emphasis on how to do the proofs with the functions like injection, surjection, and things like that. And I think for the second part, it's going to be more evenly distributed among all the topics that show up on the practice exams. I'm not going to go into quite as much detail on certain topics as I have perhaps in previous review sessions, just because all the previous review sessions have been recorded. And so if you want, like more in-depth explanation, I don't want to like repeat the explanations from previous review sessions. And so if you want like that extra detail, you're welcome to go back and check those recordings. This review session, assuming that my Zoom and everything successfully makes it through, I hope to record it as well, and I hope to post it by tomorrow. All right. So let's go ahead and get started with the actual content. I want to start by just giving you a little bit of a big picture. We're going to essentially start from a very, very simple structures, and we're going to build this up into more and more complicated things. And so at the heart of all that we have been doing is that we have been determining what mathematical statements are true and what mathematical statements are false. At the heart of everything is the notion of truth and falsehood. And so in order to reason clearly about truth and falsehood, we need a structure in which we can describe statements that are true and statements that are false. And that is the notion of propositional logic. A proposition, as I would like to review with you, is a statement which is either true or false. We can use variables to represent propositions, for example, P and Q. And unlike in algebra, in which if we have variables which represent numerical values, in algebra, we cannot possibly enumerate out all possible values for a variable. For example, if I were to give you a variable x representing a number, I wouldn't be able to physically write down on the board every single number that x could possibly represent, like 1, 2, 3, 4, 5, 6, because there are an infinite number of such values. But in propositional logic, because we're only dealing with things that are true and false, I can completely enumerate all possible values of each variable. So here I have 2 variables, P and Q, and I can enumerate all possible values, true and false, for P and Q. Just like in algebra, we're able to have operations to combine variables into more complex expressions. Similarly, in propositional logic, we're able We also have operations to combine propositions into more complicated propositions. And so that's things like P and Q, P or Q, P implies Q, P if and only if Q, and maybe I can add this one here, not P. And the way these operations are defined, they are defined by what their value is given what P and what Q is. So the definition of and essentially can be defined based on a truth table. I list out all possible values of what P and Q can be. And what's P and Q? P and Q is simply when P and Q are both true, it's true. And otherwise, it is false. Similarly, for P or Q is defined to be true whenever at least one of P and Q is true, and false if both are false. P implies Q is defined that if I know P is true, Q has to be true. If P is true but Q is false, this implication is false. If P is false, essentially the idea is that all bets are off. So P implies Q automatically is true. P if and only if Q is the same thing as P implies Q and Q implies P. And if we were to evaluate this, we would find true, false, false, true. Oh, and also not P. I'll just fill this in here. False, false, true, true. We are able to create even more complex expressions using these base operations. For example, I can also make something, say, like P implies Q and Q. And all that would simply entail is I would take the column P implies Q, I would take the column Q, and I would take the and of each corresponding row. So true and true would be true. False and false would be false. True and true, this is true, and this is false. And likewise, we can do this for more and more complex propositional expressions. A few things that I would like to point out and review to you on this truth table is I don't think it's too hard to construct this truth table, but the key insight here is that it gives you insight into how to write proofs and what you need to prove, how to prove certain statements. As a reminder, in order to prove P and Q, we need to prove that both P and Q are individually true. In order to prove that P or Q is true, all we need to do is prove that one of them is true. Then we can get that P or Q is true. In order to prove that P implies Q is true, and this is, I think, probably one of the most important ones, we assume that P is true, and we conclude that Q is true. The reason we don't have to take care of the case when P is false is because if P were false, we wouldn't have to prove anything at all. We automatically know that P implies Q is true. So the only case where there is some doubt is if P were true, can I guarantee that Q is true? And so to prove P implies Q, I need to assume P and conclude Q. So I think that's important enough. I'll write this here. So to prove P implies Q, I need to assume P, conclude Q. And to provide a counterexample for P implies Q, so counterexample, I need to give an example where P is true and Q is false. To prove P implies, so whenever you see a proof on your exam and you want to be able to structure in what implies what, P implies Q, figure out what P is, what Q is, and if you were asked to prove it, you want to assume first the P and end up with the Q. Conversely, if you're asked to give a counterexample, if that statement is in the form P implies Q, you want to figure out what your P is, you want to figure out what your Q is, and give an example. And what do you have to show for that example? You want to show that that example satisfies P and doesn't satisfy Q. To prove P implies Q is true, I need to assume P and conclude that Q is true. To show that P implies Q is false, I need to find an example where P is true, Q is false. Notice this is the only case where P implies Q is false. All other cases, P implies Q is true. So the only way to show that P implies Q is false is to find an example where P is true, Q is false. You're asked to prove P if and only if Q. This is simply proving P implies Q individually and Q implies P individually. I don't want to dwell too much more on this because we're going to do a number of examples. And in those examples of like function proofs and things like that, I think these principles are going to arise naturally. I want to now move on quickly to talk about predicates as well, which are the ideas of for all and there exists. And to talk about these predicates, I want to use a few examples. And I'm just going to use these examples to demonstrate how we are going to convert English statements into propositions, into predicates. The English statements that I have chosen are very similar to each other, but I want to demonstrate to you how these seemingly very similar English statements can result in very different predicate expressions. And so I'm going to move this board up and provide you with 4 examples that we are going to convert into predicates. So suppose S is a subset of the natural numbers. And the 4 statements, S contains only multiples of 3. S contains a multiple of 3. S contains every multiple of 3. So every multiple of 3 in the naturals. And finally, S contains exactly 1 multiple of 3. Let's do the first one together. S contains only multiples of 3. What this means is that every single element in S is a multiple of 3. So if I'm going to say every single element in S satisfies what property? It's a multiple of 3. For all S inside the set S. What do I know? It's a multiple of 3. And how do I express that little s for every element S? For every, instead of, let me just give n. For every n inside S, for every element n inside S, what do I know? I know that it's a multiple of 3. And so I'm going to write out what it means to be, for little n to be a multiple of 3. It means there exists some k inside the integers such that n is equal to 3 times k. So this part here says this is a multiple of 3. So n is a multiple of 3. And what this is saying is every single element n inside S satisfies the property that n is a multiple of 3. Second one, S contains a multiple of 3. This one says every single element in S is a multiple of 3. The second one says S contains some element which is a multiple of 3. Yeah.
Could it be valid to say, instead of there exists k in the integers, could you say x divided by 3 is the integers?
Sure. Yeah. Yeah. But yeah, I'm going to adopt this just because I like multiplication more than division. But like, I think that would be a valid way. So S contains a multiple of 3. So this one says every single element inside S is a multiple of 3. Second one says there is some element inside S which is a multiple of 3. There exists an n inside S where what? N is a multiple of 3, so the same property. Third one, S contains every multiple of 3. So what this is saying is every single multiple of 3 in the natural numbers is also inside S. Every single multiple of 3 inside the natural numbers satisfies the property that it's also inside S. So now I need to encode somehow that every single if I write for all, like, I know I want to do some kind of for all n, but I want to encode the fact that I'm doing every single multiple of 3. If I just do for all n inside n, this sort of gets all the natural numbers, but it doesn't. Somehow I want to restrict myself to only saying every multiple of 3. One way to do it, I think one way to do this, which I think is a little bit of a cop-out, is I can just define a new set like M. That's like M is the set of all like multiples of 3, and I just say that for all n in M. I'm going to show you a different way that's not going to require defining a new set. I'm going to take this bigger set for all n inside the natural numbers. And somehow, how am I going to restrict it down to every multiple of 3? I'm going to say if n is a multiple of 3, then n must be inside S. Why does this work? First of all, does this make sure that every single multiple of 3 is put inside S? It does, because every n, if I know it's a multiple of 3, I'm guaranteed it's inside S. So therefore, this statement guarantees for me, as long as I know n is a multiple of 3, I am guaranteed that n is inside S. Notice that the statement didn't require that S contain only the multiples of every multiple of 3. It just said that it has to contain every single multiple of 3. And so notice this if statement says, if I know that n is a multiple of 3, then I'm guaranteed n is inside S. And this guarantees that every single multiple of 3 is always going to be inside S. So I can, instead of writing the words, if this, then this. Now you may be wondering, when I did for all n inside the natural numbers, there are also a bunch of n which are not multiples of 3. Do I have to do anything about those things? Remember, an if statement, if the antecedent of an if statement, if the P part of the if statement is false, I still get this whole thing to be true. Therefore, if n is not a multiple of 3, this if statement automatically becomes true. It's like I don't really care if n is not a multiple of 3, whether or not it's an S. All I need to care about is S has to contain every single multiple of 3 has to be inside S. If S is not a multiple of 3, sort of all bets are off. I don't care like whether or not it's inside S. And so that's why this encoding fits this English description, because if I'm a multiple of 3, I'm guaranteed I'm inside S. If I'm not, this part is false. The whole if statement is automatically true. It doesn't really matter whether I'm inside S or not. All right, the last one, S contains exactly one multiple of 3. So here, it has to contain one multiple of 3. So there has to exist this n. This n has to, there has to exist this n. This n has to satisfy this property. It has to satisfy the property that that n is a multiple of 3. But that's not quite enough, because at this point, this is still the same as the second one. The second one says S contains a multiple of 3, but the fourth one requires that there has to be exactly one multiple of 3. So I can't stop here, because right here just says that there exists some n inside S where n is a multiple of 3. There could be, 2 multiples of 3, 3 multiples of 3, numerous multiples of 3. So how am I going to restrict now that this n is the only multiple of 3 inside S? And the way I'm going to restrict it is every other element inside S cannot be a multiple of 3. There are a few ways to encode this. I'm going to give you I'm going to give you at least one example, and if I can come up with a few more, I'll try to explain them as well. How am I going to encode that S is exactly one multiple of 3? Is that I know that it contains this n, which is a multiple of 3. And every single other element in S is not a multiple of 3. here's one way that I'm going to encode this. So my n has to satisfy this, and it has to satisfy this other property, which is that it's the only multiple of 3. And how am I going to encode this? I'm going to say, for all, say, m inside S, every element inside S, now I want to restrict only to the ones where m is not this specific multiple of 3. So if S contains, if S contains many different elements, here's my n, and then, I have all these other elements. I want to say all of these other elements are not multiples of 3. The same tactic that I used here, which was that I did the for all over a bigger set, and then to do the restriction, I made an if statement where this part gave me the restriction. Here I'm saying for all m inside S, I want to only talk about the ones that are not m. For all m inside S, I only want to talk about ones that are not n. And I want to say that these are not multiples of 3. So how do I do this kind of restriction from a bigger set S into this smaller set? Is I make an if statement. What is the antecedent of the if statement? Well, it has to be just the not, the n one. So if m is not equal to n, then m is not a multiple of 3. Not the case that, let's do, not k prime, not the case that m is a multiple of 3. So to break this down a little bit more for you, there exists this n. So how did I figure this out? I said S has to contain a multiple of 3. So I have to exist. It has to contain a multiple of 3. I have to be like some kind of there exists. There exists this n. What does that n have to satisfy? It has to be a multiple of 3. What else does it have to satisfy? Everything else can't be a multiple of 3. So it has to be that n is a multiple of 3 and what else? Everything else not a multiple of 3. How do I say everything else not a multiple of 3? Well, I have to say essentially everything else not a multiple of 3 is for all elements not n, for all elements except n, those are not multiples of 3. How do I restrict myself to only talking about the non-n elements? Is I do a for all over the bigger set S, and then I pull an if statement where the thing here is the kind of restriction to a smaller set. In other words, I do a for all on the big set S, and I'm saying, well, I actually want for all elements that are the non-n ones. So for all m inside S, non-n ones, m is not equal to n. If I know that, what do I know? Not multiple of 3. So not multiple of 3. If I want to negate this statement here, remember how do we bring the negation in? Is I bring the negation in and I flip the quantifier. So the there exists becomes a for all. And it's not the case that m is equal to 3k prime. Or equivalently, I can say this part is m not equal to 3k prime. Right. Anyone want me to kind of explain any part of this again? Yeah.
Why did you use k prime?
Oh, where is it? So why did I use integers instead of natural numbers? I mean, I think it's equally valid to do natural numbers, but I guess most generally the definition of a multiple of 3 uses the integers, so that's why I use the integers, but I don't think it would be incorrect to switch it. Right. There anybody want me to explain any part of this again? All right. So I want to now move on to a little bit about set theory. And as I mentioned in the ed post announcing the review session, I'm going to primarily focus on examples rather than talking too much about definitions and abstract like procedures and things like that. And so I'm going to erase this. I'm going to provide a few examples of sets. Maybe set A. This is a set 1, 2, 3, 4. A set B, which is a set C, which is, and I want to list out a number of operations that we're going to do. So we have power set of B, B cross C, C intersect A, C union A, and A set minus C. The first step, whenever you are dealing with these kinds of set operations, is to clearly determine what are the elements of the sets in question. I think this is an important enough principle that I want to repeat it, which is that every time you are tasked with doing this kind of set operation thing, the first thing you should do is figure out what are your sets and what are the constituent elements inside those sets. Most commonly, the mistakes that are made in doing these kinds of problems is that students get confused about which things are the set themselves and which things are the elements contained within the sets. It's not that complicated for regular elements, say like 1 and 2, or here like 3 and 4. But it can get confusing, especially when the elements themselves are other kind of structures. For example, here, if I have an element which is itself a set. So I want to clearly figure out exactly what are the elements inside these 3 sets. For C, it's fairly easy. There are 2 elements. One is 3, one is 4. For B, there is 1 element. That 1 element is this object, the set containing 1. For A, there are 3 elements, an element 1, an element 2, and an ordered pair, 3, 4. You should think about these elements themselves as some kind of like atomic object that you cannot sort of like break. Like, I don't think it would be a good idea to think about these individual elements as things which you can somehow like pull them apart. When we're doing these set operations, it's very helpful to think about these elements as like just objects that you cannot sort of break apart, that like you can't like pull this one to get a 3 and a 4 individually. So I think it will be clear if we just run through the examples. Power set of B. What is the power set? The power set is, so I want to write this here, the power set is the set containing, so the power set is itself a set. It contains as its elements, so let me write P of, let's say, a set S. Power set of S is a set containing, what are the elements of this set? Subsets of S. Therefore, the elements of power set of S, what are the elements? They are themselves sets. What sets? Subsets of S. So the power set of B is a set containing the subsets of S. What are the, or the power set of B is the set containing the subsets of B. What are the subsets of B? The way to think about this is to list out all the elements of B. I have I'm going to list it out in this fashion. So I have one element. Let me list it this way. I have one element, and I can either include it, I can either not include it, or I can include it. And then form here the set corresponding to not including and including. So here, I'm going to form the set corresponding to not including this element, which is the empty set. Or I'm going to form the set, and then so here I'm going to form the set which is including this element, which is the set containing that element. These here are my subsets of B. The elements of power set of B are the subsets of B. Therefore, there are two elements, empty set and set containing one. B cross C, the way to think about this is to list out the elements, to clearly list out the elements of B, list out the elements of C. And so what is the Cartesian product, A cross B? This is a set. The set contains individual elements. Those individual elements are ordered pairs. What do I know about these ordered pairs? The first thing in the ordered pair comes from set A. Second thing in the ordered pair comes from set B. And so the way to think about what this set is it's the set of every single ordered pair where the first thing in the ordered pair comes from my first set. Second thing in my ordered pair comes from the second set. And so what we want is every possible ordered pair, first thing from first set, second thing from second set. And so now that we have done combinatorics, we can now know that the size of B cross C is the number of elements inside B times the number of elements inside C. I'm going to now list the elements of B cross C. So I want ordered pairs. The elements of this, the elements of A cross B are ordered pairs. What do those ordered pairs look like? The first element is inside B, second element is inside C. And I want to do every possible ordered pair. Well, B only has one element, so the first element has to be the element in B. C has two elements, so there are now two possibilities for each element in B. So I have two possibilities. And the second element can be a 3 or can be a 4. C intersect A. I want to identify the elements inside C, identify the elements inside A, and figure out what elements are inside both of them. C. So one way I can do this is I can look through the elements one by one inside one of my sets and ask, is it in the other one? If I answer yes for one of those elements, then I put it inside my intersection. I'm going to demonstrate this now. C intersect A. I'm going to go through every single element inside C, and I'm going to ask, is it inside A? If it is, I'm going to add it into my intersection. If not, I'm going to keep it out of my intersection. So I'm going to go through every single element inside C and ask, is it also inside A? My first element is the number 3. Is the number 3 an element inside A? It is not, because A contains 3 elements, the number 1, the number 2, and the object ordered pair 3, 4. This is sort of the motivation for why I said to think about these like in a very atomic kind of fashion. Because even though the ordered pair contains a 3 inside and an ordered pair contains a 4 inside, this element is not a 3, nor is it a 4. It is a sort of boxed thing that is like contains 2 objects, 3, 4. And the number 3 is not the same as this boxed object containing 3 and 4. Is 3 an element inside A? It's not. Is 4 an element inside A? It's not. And so therefore, there's nothing inside the set. So this is empty set. C union A. the way to do this union is to go through every single element inside C and stick it inside my set. Then go through every element inside A and also stick it into my set. Recall that sets do not have duplicate elements, and therefore, if there's an element inside A, which is already included, there's no need to include it twice. And I would advise that on the exam, if you do run into the situation of, like, say, a duplicated element, that you don't write the element twice inside the set. So if you run into a duplicate, it's best to have every element be inside your answer once, and not to have duplicates. I don't make any promises for the rubric, but to be safe, I think it would be best not to include duplicates inside your sets. Here we don't really have the problem of duplicates because there's no elements inside both C and A. But C union A, what do? I'm going to go into C and I'm going to write down every single element inside C. The two elements, there's a 3, there's a 4. Then I'm going to go inside A and I'm going to write down every single element inside A. What are my elements inside A? Well, there's a 1, there's a 2, and there's ordered pair 3, 4. And that gives me my union. A set minus C. To do set minus, what am I going to do? I'm going to go into my set A and ask, and go through element by element inside set A and ask, is that element also an element of set C? If it is, I'm going to remove it. So I think the best way to think about this is to first take your whole set A. 1, 2, 3, 4. Go through element by element inside A and ask, is it inside C? Is 1 inside C? It's not, so we keep it. Is 2 inside C? It's not, so we keep it. Is ordered pair 3, 4 inside C? It's not, so we keep this. If there were an element that were inside, if in this process of going through one by one, there were an element inside C, then I would take it out from the set and I would progressively sort of one by one ask, is it inside C? If it is, I'm going to take it out. If it's not, I'm going to keep it. So if I were given a set, say D, and this D were, say, the set containing, or just one thing, ordered pair 3, 4, then A set minus D would be, I'm going to start with my whole set A, 1, 2, 3, 4, and I'm going to go through element by element inside A and ask, is it inside D? Is 1 inside D? It's not, so I keep it. Is 2 inside D? It's not, so I keep it. Is 3, 4 inside D? It is, so I take it away. And this remains, gives me the set 1, 2, SO. Are there any questions about this? All right, I'm going to now reverse the boards. And I'm going to proceed now to talking about relations. I want to remind you of the formalism for what a relation is. A relation over a set S. So maybe I'll say a relation R over a set S. What is the set S? Whenever a relation in its kind of most general sense is that we're relating elements together. we're saying, element A is related to element B. Element C is related to element D. A relation. So what is the set S? The set S tells me what are the objects that I'm relating together. From what set contains the elements that I'm going to be like relating together? And so the formalism for a relation R over a set S is the relation itself is a set. And what are the elements inside my relation? They're ordered pairs, x, y. X has to be inside S. Y has to be inside S. And what does the set of ordered pairs describe? It describes every single pair of x, y, where x is related to y. Recall that in a relation, it is not necessarily symmetric. Therefore, by saying x is related to y, that is different from y is related to x. That difference is also what motivates why I'm using an ordered pair. The ordered pair xy is different from the ordered pair yx. These two things are not the same. I want to remind you the definitions of a few properties of relations. That's reflexive, symmetric, antisymmetric, and transitive. I'm going to write down the definitions first and then explain a little bit of the intuition and how to think about these. So reflexive, for all elements inside my set S, the ordered pair XX, the same x here and here, is inside my relation. For all x, y inside set S, if x is related to y, then y is related to x. Antisymmetric, for all x, y inside S, if x is related to y and y is related to x, then x is equal to y. Transitive, for all x, y, z inside S, if x is related to y, y is related to z, then x is related to z. I want to have you take note of the fact that most of these statements are if-then statements. P implies Q statements. For example, here's my P implies here's my Q. I want to now give a few examples. Let's say my set S is the set 1, 2, and 3. And I want to find a relation R which is reflexive, symmetric, transitive. And recall that this is also the definition for an equivalence relation. So in effect, I want something that kind of captures the notion of equals. So I can write a set like this. This is a relation. What this relation says is 1 is related to 1, 2 is related to 2, 3 is related to 3. However, if I had 1 and 2, 1 is not related to 2, nor is 2 related to 1. I want to make sure that the set that I wrote down is actually satisfies the required properties. Is it reflexive? Reflexive says that for every single element inside S, for every single element 1, 2, 3, XX has to be inside the relation. So 1, 1 has to be inside the relation, 2, 2 has to be inside, 3, 3 has to be inside, and that is the case. Symmetric. If I know that XY is inside the relation, then it's swap. YX has to also be inside. I know one, so 1 is inside, and its swap is inside. 2 2 the same, 3 3 the same. Why do I not need to worry about, say, like 1 2 and 2 1? Because 1 2 is not even inside the relation. If 1 2 is not inside the relation, antecedent is false, whole statement, if statement is true, and therefore there's sort of nothing to check. This if statement is automatically true if I'm talking about, say, like 1 2, because 1 2 is not even in the relation. This part is false, the whole if statement automatically true. So to check when whether your if statement is true, the thing you really have to check is when this part is true, do I automatically get this part is true? If I don't have to check the cases where this part is false, because when this part is false, my if statement is automatically true. I only need to check the cases where when this is true, do I get this is true? Is this transitive? If xy is inside R and yz is inside R, do I get xz inside R? That is the case. I'm not going to go through like every single pair, but you're welcome to check that this relation is in fact transitive. I want to give a different example. Can we find an example which is, I'm going to change it to a different set here. Let's do this is an S1. I'm going to now do a different set, S2. And the set S2 is going to be 1, 2, 3, 4. And I want to find one which is transitive only. Now, when preparing for this, I already wrote down what I think is a correct answer to this problem, but I want to essentially sort of do it in front of you to show you sort of what are the things that I'm thinking of. One special case of relation, which sort of starts to come up with all kinds of like weird, unexpected situations, is the empty relation. So my empty relation, this is always a sort of good example to check, which is the empty relation is just the empty set. What do I know about the empty set? If my set is 1, 2, 3, 4, is my empty set reflexive? So not reflexive, because reflexive requires, say, like 1, 1 to be inside this set. 2, 2 has to be inside. 3, 3 has to be inside. 4, 4 has to be inside. None of those are the case. Definitely not reflexive. Is it symmetric? How many people think it's symmetric? So can I have a show of hands? Who thinks it's symmetric? And who thinks it's not? And who is not voting? All right. So the empty relation is in fact symmetric. And the reason is, for all x, y inside S, if x, y is inside the relation, is x, y ever inside the relation? Never inside the relation. This part always false. This if statement always true. Oh, anti-symmetric. Who thinks it's anti-symmetric? And who thinks it's not? And who is unsure? All right. It's also not it's also anti-symmetric. If xy is inside R and yx is inside R, when is xy inside empty relation? Never. When is yx inside empty relation? Never. When is this true? Never true. Always false, which this thing always false, which means this if statement always true. Similarly, empty relation also transitive. When is this true? Never true. This is if statement always true. The antecedent is always false. Therefore, the total if statement is always true. So here for this transitive only, it's always a good idea to check like some weird case like this empty relation just to see if it works. For transitive only, I can't use the empty relation because it's also symmetric and anti-symmetric. So I have to put something inside my relation. So it has to be non-empty. So let's just put in something kind of, and second thing, if I want to be transitive only, well, even, I won't go there yet, but like for transitive only, I have to put something inside my relation. So I'm just going to throw something in like, 1, 2. But if 1, 2 is inside, I also, okay, so now I have 1, 2 inside here. It's still transitive because I never actually get the case where x, y, and y, z are inside R. I never get like a 1, 2, and then 2 something inside R. So this part is still never true. And therefore, the whole statement is still always true because this antecedent part is still never true. I'm still okay. I'm still transitive. But sort of the one key thing here is I have to be not anti-symmetric, not symmetric, not reflexive. If I want something to be not anti-symmetric, I have to have something where this is satisfied and this is not. Recall that the only way to show like an if statement is false is to have this part be true, this part be false. So I need somehow to still get this part to be true, this part to be false. So now with this 1, 2 inside, I have to add in a 2, 1. Because I needed to get this x, y inside R and yx inside R, and x is not equal to y. So I had to add in this 2, 1. And why did I have to add in this 2, 1 is because I had to like get this antecedent to be true and also this false. So now this part gives me my not anti-symmetric. So this part, I got my not anti-symmetric. But I can't end it here. Because the issue now is that, does this work? This doesn't work because I violated transitivity. Transitivity says if x, y, and y, z are inside R, then x, z has to be inside R. Well, I have 1, 2, and then I have 2, 1. Which means if I want to be transitive, I also need 1, 1. So now this part, so now I'm okay with transitivity because I can do 1, 1, 1, 2. I still get 1, 2. I can do 1, 1. I can do 1, 2, 2, 1. I still get 1, 1. This part is okay transitivity. So now this is transitive. I still got my not anti-symmetric. That's right here. But is this symmetric? This relation is symmetric because if I know x, y is inside R, do I always get the swap is inside R? Well, 1, 2 is inside, so its swap is inside. 2, 1 is inside, its swap is inside. 1, 1 is inside, its swap is inside. This is now symmetric. So somehow I have to break the symmetry as well. And so what am I going to do? I need to add another element so that I can break my symmetry. And the simplest element to add in is to add in something like 3, 4. Why didn't I add in something like, what if I added in something like 2, 3? The reason I didn't add in something like 2, 3 is because this could end up in like a huge other kind of can of worms. Because now like transitivity is broken again because I have 1, 2, 2, 3. So I need to add in 1, 3. And then once I add in 1, 3, then I have 2, 1, 1, 3, and I get another 2, 3 that I have to add in, or 2, 3s here. So like there's sort of some cascading effect here. But if I want to break symmetry, I'm just going to put in, say, something like 3, 4, and not 4, 3. This 3, 4 is sitting here breaking my symmetry, so it's not symmetric. Now I'm going to check, is this transitive? So I know it's not symmetric, not anti-symmetric. Is it reflexive? It's not reflexive. Why is it not reflexive? Reflexive says every single element inside S, the pair XX has to be inside my relation. Even though 1, 1 is inside my relation, reflexive requires every single element inside S, that pair XX to be inside a relation. So it means that 1, 1 has to be inside, 2, 2 has to be inside, 3, 3 has to be inside, 4, 4 has to be inside, 2, 2 is not inside, 3, 3 is not inside, 4, 4 is not inside, not reflexive. This thing, not reflexive. Is it transitive? Well, I already checked this case of like the 1, 2, 2, 1 gets me 1, 1. We're good. 1, 1, 1, 2 gets me 1, 2. We're still good. 2, 1, 1, 1. That gets me 2, 1. We're still good. So all the interactions here keep me inside transitive. When I add this in, are there any issues? No issues with transitive, because when I add this in, it sort of, quote unquote, doesn't interact with the other elements. My transitive, I needed like a x, y, y, z. I had to have the same element here and here. But 3, 4 just kind of never appeared here anyway. So 3, 4 is not interacting with this stuff in terms of transitivity. And so by adding in 3, 4, this stuff satisfies transitivity. 3, 4 doesn't make additional cases where this antecedent becomes true. And so I don't have to check anything for 3, 4 interacting with anything else. Yeah.
What 2, 1, 1, 2?
Oh, you're right. So 2, 1, 1, 2 is right. So thanks for pointing that out. So 2, 1, 1, 2. So we still need to add in a 2, 2 here. Is there anything else that? So it's still not reflexive. So still not reflexive. This 2, 2 gives me transitivity. So all of this, I think, assuming I didn't miss anything, I think all of this gives me transitivity. The 3, 4 doesn't affect anything because the 3, 4 doesn't affect these in terms of its antecedent. And so I think this is now transitive. It's not reflexive because still 3, 3 and 4, 4 are not inside. It's not anti-symmetric because 1, 2 and 2, 1 are inside, but 1 is not equal to 2. And it's also not symmetric because 3, 4 is inside, but 4, 3 is not. Right, I know this is kind of a confusing, it's kind of a lot going on. Any quick questions about this? Yeah.
And why it's not reflexive again.
Oh, why it's not reflexive? Yeah, so reflexive requires for every single element inside my set S, the pair XX containing the same two elements has to be inside R. So it means that every single element inside S has to have the property that XX has to be inside my relation. 1, 1 has to be inside, therefore. 2, 2 has to be inside. 3, 3 has to be inside. 4, 4 has to be inside. 3, 3 and 4, 4 are not, and therefore it's not reflexive. Right. Yeah.
Why couldn't we just the relation 1, 2, 2, 3, and 1, 3?
Oh, I'm not gonna quite work it out like on the board exactly, but I'm sure there are other examples that will work, and probably simpler than this one. But I just wanted to sort of go through once sort of what would be like a possible thought process when you're like working through a problem of this type. Yeah.
To add on the previous question, I also had that initially it doesn't work because it creates the antecedent default scenario for like anti-symmetric, for example, which means you satisfy the condition and it's still anti-symmetric. Because you want it to be only
Right.
Yes, I have
Oh, I think the 1, 2. Oh, because you'll never get the antecedent of anti-symmetric to be true. Right. Right. Yeah. I think we can talk about this a little more offline. Yeah. And
why did you add 2, 2?
oh, why did I add 2, 2 was because I had 2, 1 and 1, 2. So looking at my transitivity, I had 2, 1 and 1, 2. So therefore I had 2, 1 and 1, 2. So therefore 2, 2 had to also be inside. All right. I want to get to the last kind of topic in this part, which I think is one of the most important ones, which is how to work through a proof involving injection and surjection. And it's like looking at the practice exam, there seems to be one whole problem involving that of substantial length, so I want to be able to have time to work through an example like that. So I'm going to switch the boards. If there are still additional questions, we can talk about them after, but I want to be able to cover everything within the time. So here. I want to do a lightning fast review of the pertinent definitions for functions. A function, essentially, I want to think about, I just want to you to think about a function as a sort of mapping this between a set D to a set C. D we call the domain, C we call the codomain. You can think about them, a function, as somehow like these arrows. Recall that a function, the word function, places very strict requirements on what the arrows need to look like inside D. For a function, the word function automatically means that every element in D has exactly one arrow pointing out of it. And recall that a function, when we have a function, there are very strict requirements for what happens in D and very loose requirements for what happens in C. The word function indicates that every element inside D has exactly one arrow pointing out of it, but places almost no restrictions on what happens with the arrows as they enter C. In order to place greater restriction on what happens when arrows come into C, that is the motivation for the words injection, surjection, bijection. Injection, at most one arrow. So let me rewrite this as every element in C has at most one arrow pointing to it. Surjection, every element in C has at least one arrow pointing to it. Bijection is injection and surjection, every element, so the same, has exactly one arrow pointing to it. So here's at most one, at least one, and exactly one. I want to do for you an example. Actually, before I do for you the example, I will write out the technical definitions. So if f is a function, an injection says for all D1, D2 inside the domain, f of D1 equals f of D2 implies D1 is equal to D2. Intuition here, if I have two elements here and they point to the same thing inside C, so if I had like a D1 and D2, if they were to point to the same element inside C, then D1 would have to equal D2. Specifically, this definition forbids this thing from happening. I can't have f of D1 equals f of D2 but D1 not equals to D2, because this would be some element in C has 2 arrows pointing to it. And so this definition specifically forbids this thing from happening. I can't have f of D1 equals f of D2 and D1 not equals to D2. So if I have f of D1 equals f of D2, I know that these two elements have to actually be like the same. Surjection. For all C inside C, there exists D inside D, where f of D is equal to C. What this says is that every single element, let me make this diagram a little cleaner. Every single element inside my codomain, for every element inside my codomain, there has to exist something over here pointing to it. Has to exist this for every C inside my codomain, there has to exist this D here, where f of D is equal to C. There could be, multiple of these, but I can't have an empty one. Because in this case, if I had an empty one, then I would have some C where there is no D pointing to it. This definition forbids this from happening. And therefore, every element has to have at least one arrow pointing to it. It forbids the fact that I have no arrows pointing to it. And bijection is simply the and of the previous two. I want to now proceed to the example. The example that I'm going to do is one that is one that I believe you have already done inside the discussion, but I want to review it and just sort of go through again the thought process of how to think about how to piece each thing together and how to clearly kind of like weasel your way out in one of these proofs. I'm going to, I'll do the example here. So this example is, you're given 3 functions. F goes from W to X. G goes from X to Y. H goes from Y to Z. And we are going to prove that if G composed with F is a bijection, and H composed with G is a bijection, then H composed G composed with F is also a bijection. I'm going to, for the sake of this proof, I'm going to split this up. So just say that H is injection and surjection. So in effect, there's going to be 2 parts to this. The 2 parts are to prove first, H of G of F is an injection, H of G of F is a surjection. It can be difficult to sort of reason about this, even visualize this even very clearly. And so the first step I like to do when I'm presented with this kind of a composite function business is to draw out these kind of diagrams showing how things are moving in between the sets. So here I'm going to do my W, my X, my Y, my Z. And so F is essentially a function that moves from here to here. So F is something like this. G is something that moves from here to here. H is something that moves from here to here. And I know that G composed with F. So remember, when I have composition, I have to read this from right to left, which means that my element, so G composed with F, the way the mnemonic to think about it is like, it's like a G of F of something. So my input goes into F first, then G. If my input is going into F, G composed with F is a function from what domain to what codomain. It has to go into F first, so it has to be in the domain of F. So it's in set W. Then my input here is in set W. It goes through F. It's going to end up in set X. Then it's going to go through G, end up in set Y. So this is from W to Y. H composed with G. What is this? This is like an H of G of something. So I have an element here. It has to go into G, which means that it has to be in G's domain, X. And then it's going to move. It's going to follow G. It's going to go to Y. And then it's going to go into H. It's going to go to Z. So X goes to Z. And what's h of g of f? Well, this is like an h of g of f of something. It's going to have to, something, the input here has to go into f, so it has to start in w. Then it's going to go into f to x, into g into y, into h into z. So it's going to end up inside z. So whenever you're dealing with maybe something that's, if you get something that's kind of confusing like this with lots of domains and codomains, it always helps first to clearly establish what the domain and codomain are of all of the functions that we are talking about. If you do not do this, there is a very, very good chance you will get confused. And you will have the wrong elements inside the wrong sets, and your proof will very quickly disintegrate into like a very confusing attempt. And so I strongly advise, if you are presented with a very complicated setup like this, with multiple sets, multiple codomains, functions moving in between different sets, is to clearly establish first what are the domains and codomains of each of the functions that you are talking about. So not just like f, g, h, but if you have a g composed of f, h composed of g, all of these things, first establish what your domains and codomains are. Now I'm going to proceed to do the proof. So I'm going to first prove h composed of g composed of f is an injection. I'll just write this here. So this is for the injections part. The key thing now to remember, what are you assuming? What are we proving? We want to prove h of g of f is an injection and a surjection. And so if you recall that to prove an and statement, we're going to prove them each individually. We're going to prove the injection part individually, and we're going to prove the surjection part individually. The key thing to first remember, what am I assuming? Where do I want to end up? Especially for a function proof like this, I again want to recommend and reiterate the benefit of working through these proofs, not just top down, but top down and bottom up. Think about what you know and think about where I want to end up. What's my goal? Where do I want to end up? If you don't write the bottom up part, in order to do it correctly, that whole bottom up part has to be inside your head. And so rather than try to keep the whole kind of bottom up part inside your head, I think it's especially helpful just to write out the bottom up part. In particular, the grader is looking for a certain kind of setup that corresponds to this way that I'm going to present to you. Now, and so it's very helpful, I think, to think about it this way, so that not only is it helpful for you to get the problem correct, but also helpful for the grader to easily give you partial credit. It may not always be the case that you will ask to prove that something is an injection or a surjection. I looked through both of the practice tests, and one of them actually asks you to prove that something is the identity or things like that. And so it's important that if you're asked to do something of that sort, that you still figure out, what am I assuming? Where do I want to end up? Even if you're not asked to prove the injection, surjection, but you just prove that this function is the identity function, or prove that this function satisfies this other property, you want to make sure that you're still keeping in mind, what am I assuming? What am I proving? In this case, what am I assuming? I'm assuming this, g of f is a bijection, h of g is a bijection, and I'm proving h of g of f is an injection. So we're working on this. We're going on this side here first. We're going to assume this, prove this. So assume g of f, bijection, h of g bijection. And I want to prove h of g of f is a bijection. Whenever you're presented with something like this, it's always helpful to write things out in terms of the definitions, in terms of the propositional logic definitions, which is why I presented not just the intuitive manner of thinking about injection, surjection, but also the formal manner of thinking about them. These will guide you sort of into the right inroads into how to approach this proof. Or, oh, not bijection here, injection. What's proving h of g of x is an injection? I'm going to look at my definition, and I'm going to rewrite it in terms of the problem here. For all d1 and d2 inside the domain, well, what's my domain of this? I think that's where it comes into it comes in handy that we clearly notated what the domains and the codomains are of each of the functions that we're talking about. Is the mic still working, by the way, or like can people still hear me in the back? All right, it's good. H of g of f is an injection. I'm going to write out this definition here. So what do I actually want to prove for injection? For all d1 and d2 inside the domain, what's my domain? W. So I'm going to. So a convention I like to use is to just use variables that correspond to the set. So I'm going to say for all w1, w2 inside w, if f if h of g of f of w1 equals h of g of f of w2, this implies w1 equals w2. Immediately, this predicate kind of goal gives me a lot of insight into how to write this proof. Because this is a for all statement. How do I prove a for all statement? The first thing I write down. Please do this. If you see a for all statement, two things to write down. Take an arbitrary this. Take arbitrary this. And what do you want W1 and W2 to satisfy? This property right at the bottom. Once you see, so what were the steps here? I said injection. What's the definition? This is the definition. This is a for all statement. Once I see the for all statement, I take an arbitrary this. I conclude this. This is my new goal. To prove a for all statement, I have to take an arbitrary this and conclude this. This is my new goal. What kind of a statement is this? It's an if statement. P implies Q. How do I prove P implies Q? Assume P. Conclude Q. Notice now here I've now shrunk my goal down to just proving, I just need W1 equals W2. I've assumed this and assumed this. So I have, this is like the material I can use. And I want to show that this is true. Even reasoning about this is still kind of difficult because we still have like, all this H and G and F going on. But the way I like to think about it is, I'm going to come back to this diagram that I have here. If I know H of G of F of W1 and H of G of F of W2 are the same, that means they're both, ending up in the same element here in Z. W1 and W2 are being mapped to the same element here in Z. What do I know now is that G composed with F is a bijection, H composed with G is a bijection. So I want to somehow piece together like the things that I know to conclude new things. If I know H composed with G is a bijection, that means I know this is an injection and a surjection. I know this is also injection and surjection. And so I'm going to take advantage. So somehow I want to, take this, equal here and kind of backtrack it all the way down to here where I can get W1 equals W2. Well, in order to make some progress in that backtracking, notice H composed with G is a bijection. which means it's an injection. So h of g of this equals h of g of this. By definition, h of g of this equals h of g of the other thing. Means that those two things are equal. Means f of w1 equals f of w2. So we have now, w1, w2 kind of here. We want to show that these two things are actually equal. And we know that, these two come here. And they also, follow like up to here. So both of these, come up to the same element here. And we know they're equal here too. F of w1 equals f of w2. Now how do I get back to w1 equals w2? Well, I can't say that, oh, f is an injection. I didn't assume f is an injection. Well, it'd be nice if f were an injection because then I could just conclude it immediately. But I didn't have f as an injection as something that I knew. All I have is g composed with f as an injection. So somehow I want to use additional pieces of information, particularly the stuff that I haven't used yet, in order to conclude this. And one thing that I haven't used yet is g composed with f as an injection. So how do I sort of manipulate, twist this thing so that I can use the fact that g composed with f is an injection? Well, I would need it to say something like g of f of something equals g of f of something else. I have this. I can just apply g to both sides. Oh, and now that looks like this. I get this because g composed with f is an injection. Why is it the case that from here I can do this to here? That recalls the definition that comes in from the word function. The word function says every element has exactly one arrow pointing out of it. So f of w1 and f of w2, if f of w1 and f of w2 are the same element, each element has exactly one arrow coming out of it. So therefore, g of f of w1 and g of f of w2 have to also be the same because there has to be exactly one arrow coming out of this element f of w1, which is also the same as f of w2. This essentially completes the proof. I assume these two things. I took an arbitrary w1, w2. I assumed this. Here to here, I used that h composed with g as an injection. Here I did the definition of function. So this is definition of function for g. And from here, I used that g of f was an injection to get here. Therefore, I assumed this, I concluded this. Therefore, this implies this, this implies this. I took an arbitrary w1, w2 and concluded this property. So for all w1, w2, I get this property. This is simply definition that h of g of f is an injection. Other direction, or surjection. Again, we're assuming the same thing. G composed with f, h composed with g bijections. Make sure I'm not out of frame. All right. What do I want to end up with? I want to end up with h composed with g composed with f is a surjection. What are my strategies for how to get my way into the middle? Use some definitions to kind of clarify what my goal is. What's this? A surjection. I'm going to write out this definition for all C inside the codomain. Well, what's my codomain? Codomain is Z. For all Z inside Z, there exists an element inside my domain. My domain is W. There exists W inside W such that h of g of f of w equals Z. I want to clear up this a little bit so that it will be a little more clear. How do I prove this? I know this is my goal. What kind of a statement is it? It's a for all statement. It's a for all statement. First thing I write, take an arbitrary Z inside Z. What's the property? This is the property. I want there exists W inside W, where h of g of f of w equals to Z. the way to prove a there exists statement, is to give an example and show that it works. So I want to emphasize very clearly the components that are essential here in the surjection proof. Assume the things that you know, conclude the things you want to show, write out the definitions. The definition of a surjection is always a for all statement with this property. To prove a for all statement, please write, take an arbitrary, z inside z, c inside codomain, and what do you want to show? There exists this w where f of g of f of w equals z. Please make sure that if you prove a surjection, you have these components. Writing out this for all statement, taking an arbitrary this, ending up with this. I want to now look at this bubble diagram and say, how am I going to reason about this visually? With any arbitrary z inside here, there has to exist this w inside here, where I can, come all the way over like this. H of g of f of w equals z. The way to show that there exists this w, in its pure sense, the way to show a there exists statement is to first say, here's how I'm going to find my w. And then say, does my w actually satisfy this? Now this here's how I'm so the intuition is any z that I give you, I'm going to follow this procedure of if I were to hand you this z, I'm going to follow this procedure of using that z to figure out a w. And I'm going to say this w, I'm going to show you that this w points all the way to z. So there are essentially two steps here. Step one is to give that procedure of if I were to hand you a z, how would I find that corresponding w? And the second part is to say, this procedure that I'm going to specify, does it actually get me h of g of f of w equals z? If I just said, oh, just pick a random w, it'll be fine. Well, it's not fine because that is a procedure, but h of g of f of w may not equal to the z. So here I want to first give that right procedure and then show that h of g of f of w equals z. And this is, I think, kind of tricky. How am I going to find this w? Now, let's think about what we haven't used yet. Haven't used g of f as a bijection, h of g is a bijection. In particular, we haven't used the fact that this is a surjection, this is a surjection. So you remember this is injection, surjection. So I have a z here. Well, I know h composed, so this is, remember, f, g, h. I know h composed of g, this thing, is a surjection. So there has to be some x at least here. So I have my f function. So there has to be some x here that's pointing to the z. This comes because h of g is a surjection. So I know that there exists an x such that h of g of x equals z. And this is because h composed of g is a surjection. Now, how do I get? Now, I actually want a w which points all the way here. How do I get a w? I have this x, but I can't just say, oh, f is a surjection because I don't even know f is a surjection. I only know g composed with f is a surjection. So the only thing I can probably do is somehow I have to get myself into y, and then I can get a w. So let's say, so how do I get myself now into the y set so that I can use g composed with f as a surjection? The only thing I can think of is to do g of x. So let y equals to g of x. And then if y is equal to g of x, then I know, oh, g of f is a surjection. There exists a w such that g of f of y, g of f of w is equal to y. So I know that there is this w where, g of f of w gives me y. Does this w work? Let's just test it out a little bit. What's h of g of f of w? Well, g of f of w, that's y. What's y? That's g of x. What's g of x? Well, what's h of g of x? That's z. Therefore, this is the w that I need. So to show you where my two parts are, this is showing how to get my w, how to get w. So this is the procedure in effect. And this is showing my procedure works. How do I find my w? Well, if I'm given a z, I know g composed with h is a bijection, is a surjection. So I know I can, come back here and get my x. This x points, g of x, h of g of x gets me z. Once I get my x, then I can plug it into g again and to get a y. And then because I know g composed with f is a surjection, I know I can backtrack here to get a w. That's the w that I want. Because what's h of g of f? So this is my procedure for generating my w, is to do my backtracking on h of g, plug this into g, get a y, backtrack again to w from g composed with f. So start with my z, backtrack here to my x based on my h of g, h composed with g being a surjection. Then plug in my x to g to get a y here. And then backtrack again using g composed with f being a surjection to get my w here. That is the w that I want. Because when I plug that w into h of g of x, h of g of f, when I plug in that w following this procedure, when I plug in that w into h of g of f of w is just y. Y is g of x, and h of g of x is z. Therefore, this procedure of getting me a w always can satisfy the fact that h of g of f of w equals z. Therefore, there exists a w where h of g of f of w equals z. And since I took an arbitrary z and satisfies this property, for every z, this property is satisfied. Therefore, h of g of f is a surjection. All right, so that concludes the material I want to cover for this first part. I think we can take maybe a 5 minutes break, and then I'll resume with the second part on combinatorics and probability.
Yeah.
Sure, I can capture this out.
Wait, how do you?
I'm done with this.
Are you going? Can you give this? So I'm so he's generous.
Maybe after, is it okay? So that, yeah.
Just not. And
All right, I think I'll go ahead and get started. So the second part, I want to cover mostly this combinatorics and probability material. And I want to begin with the proportion of time I want to cover our different topics. I hope will be close to the proportion of time, the proportion of the exam that covers those topics. And so instead of going through a lot about combinatorics as I did in the previous review session, I'm just going to go over one example of a combinatorial proof. And the example that I'm going to give, this is a combinatorial proof. And the example that I'm going to give is this identity, 0 to R. I believe there's a name for this. It's called van der Waals identity. But I want to now demonstrate for you what a combinatorial proof of this identity will look like. From what I can see on the practice exams, it seems like the general structure will be laid out for you, and you would need to fill in the various components. But here I'm just going to lay out again what I think you will see on the test, which will be what will be the general structure of this combinatorial proof. Combinatorial proof always contains 3 components. 1, a counting problem. 2, the left-hand side solution to 1. And part 3, right-hand side solution to 1. The intuition behind why this works is I'm going to specify this is in effect a reverse engineering problem. Normally, you're presented with a counting problem for which you need to figure out, how many of something there are. In a combinatorial proof, you're effectively doing the reverse process. You're being given 2 answers, this and this. And what you need to do is you now need to figure out a counting problem for which the answer is this and this. Why is that sufficient to prove this identity? It's because you supplied one counting problem. So step 1 is you supplied one counting problem. Step 2 is you explain why the answer to your counting problem is this. Step 3, you explain why your answer to your counting problem is this. And because you only specify one counting problem, your counting problem cannot have multiple answers. Therefore, if the left-hand side is an answer to their counting problem and your right-hand side is an answer to your counting problem, they must be equal. So now that I'm given this identity that I'm asked to prove, step 1 is I want to figure out a counting problem for which both of these are the answer. My general advice for figuring out the counting problem that you want to use. So on the exam, I believe the problem is like already split up into part 1, 2, and 3. But my general advice for how to figure out part 1 is to look at one side of your equation and just make a counting problem that very naturally fits that one side. And then the hard part is just engineering your engineering it in a way so that you can now the hard part is solving your counting problem in a kind of clever manipulative way in order to get the other side. In other words, when you're presented with this combinatorial proof, my advice is to look at one side of the equation and just look at that and come up with the most natural counting problem you can where that is the answer. If you do that, you automatically it's not only like a good way to solve a problem like this, it's also a good way to get partial credit, because not only will you have done part one, you will have also done one of the other two parts, because you looked at one side of the equation and you just came up with the most natural counting problem for which, that is the answer. And so now essentially you've already solved two parts of this problem. You figured out a counting problem, and you figured out how one side gives the answer to your counting problem. My general advice is, if you look at two sides and you see one side that's simpler, pick the simpler side and just make a really natural counting problem for that. Right here, we have two sides. I'm looking at this. This side looks really complicated. This is really simple. I'm just going to come up with a counting problem where this is the answer. M plus n, choose R. This notion of choose, I want to give you a little bit of, as I think I mentioned this like briefly in the previous review session as well, but this notion of choose, one way to think about it is to think about it in terms of a formula of factorials and things like that. But the other way I think, which may be more natural for thinking about it in this case, is if I have, say, like n choose k, to think about this as n choose k is a symbol, is a number. This symbol n choose k represents, what does it represent? It represents the answer to the counting problem. How many? I want to write. I think it's hard to see in the back, and I think it's also maybe difficult to show up on Zoom. So I'm going to write a little bigger. So n choose k is how many subsets of size k in a set of size n. In other words, one way to think about n choose k is n choose k is the answer to the counting problem. How many subsets of size k are there in a set of size n? Therefore, if I want an answer of n choose k, I should set up a counting problem that asks me to count how many subsets of size k there are in a set of size n. In this case, m plus n choose R. I want to set up a counting problem for which the answer is m plus n choose R. Remember, the symbol n choose k is simply the answer to the counting problem. How many subsets of size k are there in a set of size n? Therefore, if I am given an m plus n choose R, if I want that to be the answer, the counting problem should be how many subsets of size R are there in a set of size m plus n? So my counting problem is the number of subsets of size R in a set of size m plus n. I believe you will be asked to supply your counting problem in the form of a set, and you will be asked to describe that set without words, but only in like mathematical notation. And so I also want to demonstrate that for you here. So what you are going to be asked on the test to do is you're going to be asked to, in part one, provide a set for which the size of the set, the number of elements in that set, is this kind of enumeration. So in other words, if I'm trying to count the number of subsets of size R in a set of size m plus n, the set of objects that I'm counting, the set of things that I'm counting that I want to provide are the set of subsets of size R in a set of size m plus n. And so essentially the set that I'm counting here is the set containing subsets S such that S is a subset of a bigger set. The cardinality of S is equal to R. Cardinality of A is equal to m plus n. I think a different way to write this would be to say something like is to say A is the cardinality of set A. So alternatively, you can say the cardinality of set A is m plus n, and you want to count. So what are you counting? You're counting the set of subsets S, where the size of the subset is R. Notice here, I've done problem 1. I've done part 1, but part 3 is just by definition of m plus n choose R. M plus n choose R is simply the number of ways to, the definition of m plus n choose R is simply the number of subsets of size R from a set of size m plus n. Therefore, I've now I've solved 2 parts of this problem. I looked at the easier side and I'm saying, what's the most natural counting problem I can figure out which answer m plus n choose R? Most naturally, as I just follow the definition, I just say, oh, number of subsets of size R in a set of size m plus n. And so automatically I get, oh, the right-hand side is the answer to this counting problem, just simply like by definition of m plus n choose R. The hard part now is to figure out why the left-hand side counts this quantity. There are a few key aspects that I think we want to look at inside the left-hand side. I can't guarantee that on the exam that part 1 and something like part 3 is going to like pop out so easily, but I think it's still a good tip to, when you're figuring out this kind of step 1, to just like laser in on one side, figure out the most natural counting problem to get your answer for that one side. Just write that down, and then you automatically will have solved sort of like either 2 or 3. So if you just kind of laser in on the left-hand side, figure out the most natural counting problem you can make for which the left-hand side is the answer, then you will have solved problem 1, and you would have solved 2 because you would have already you literally made your counting problem so that the left-hand side was the answer. So I think that principle still applies, even though it may not arise so easily as we had here. So now that we did this part 1 and part 3, let's do part 2. How does this count this? A few things to notice. I see a sum. There's a sum. That means that I have cases. If I have a sum here, if I'm adding stuff up, there could be a sigma notation where you're adding like a lot of things up there. You could just have something plus something else. As long as there's adding going on, it means I have cases. So this sum here indicates I have cases. What are my cases? My cases run from k equals 0 to k equals r. So here I have some cases, k equals 0 to k equals r. And what's this quantity? Well, this quantity corresponds to the number of things that I'm counting. So here in this case, I'm counting subsets of size r. This quantity is the number of subsets of size r for case k equals 0. And then I have another number of subsets of size r for case k equals 1, for case k equals 2. Keep in mind, one thing to remember is that the cases, they must be disjoint. And that's why I get to just add them up. If the cases have overlap, then I need to use inclusion exclusion. So if you see a sum, if you just see a sum, just stuff being added up, you want to say, okay, I need some disjoint cases. So here I have some k equals 0 to k equals r. And for k equals 0, well, I have some, so k equals 0 is some case. And in k equals 0, I have how many subsets? I have m choose 0, n choose r. For the k equals 1 case, I have an m choose 1, n choose r minus 1, and so on. And so my next goal is, I know there are cases. What does this variable k represent? I'm unable to really give you a really surefire algorithm to figure stuff out, but I want to, as I work through this, sort of give you the thought process that is going inside my head. so that I know, so that you can have some kind of like guidepost to figure out your way through a combinatorial proof. How do I figure out what K represents? I look at this term here, M choose 0, N choose R. I look at this term here, M choose 1, N choose R minus 1. It seems like what's going on is I have to pick, I pick nothing, or maybe like it would be clear if I even do like K equals 2. Is like M choose 2, N choose R minus 2. Make sure this writing is big enough. Like what is, like, for my K equals 2 case, there are M choose 2 times N choose R minus 2 possibilities. And so I'm thinking, okay, so M choose 2, I'm picking 2 things from a set of size M. And multiplied by, I'm picking R minus 2 things from a set of size N. I'm picking, I'm picking 2, I first have a set of size M. And I need to pick 2 things from there. And for every choice of 2 objects inside my set of size M, I also have another set of size N here, from which I'm picking R minus 2 of them. So I have, maybe here maybe I have R minus 2 of them. Here I have 2 of them. Let me make sure I write big enough. So here I have 2 things. I have R minus 2. So here I have so what it seems like is I have a set of size M from which I have to pick 2 objects. And then adjoining to it, I have a set of size N from which I have to pick R minus 2 objects. And why are there M choose 2 times N choose R minus 2 is because for every choice of 2 objects in M, I have N choose R minus 2 choices for what I could pick from size N, from the set of size N. For every selection of 2 objects in size M, for every possibility of 2 objects that I pick from this set of size M, I have N choose R minus 2 options for picking a set of size R minus 2 from the set of size N. And that's why I get to multiply them together. So I think the procedure now hopefully is becoming clear is that I have the set of size M, I have the set of size N, and in the K equals 2 case, I pick 2 things from here, I pick R minus 2 things from here, and I combine them together. And if I combine them together, to get a set or a subset of size R. Notice how this is starting to look a lot like my counting problem. The set that I'm wanting to pick from is a set of size M plus N. What happened here? I partitioned my set into size M, into a set of size M. So what happened here is I took my set of size M plus N. So this is a set of size M plus N. And I partitioned it. Here is size M, here is size N. And from this part, I picked 2 objects, or in general, I picked K objects. In this part, I picked R minus K objects. And I combined them together to get a subset of size R. So what's my K? What's my case's K? What does that K represent? It represents how many objects am I picking from this first section. How many objects am I picking from my first section? And how many can I pick? Well, I can pick 0 of them from the first section. Pick 1, I can pick 2, all the way up to R. Because I want to pick a subset of total size R. So I can pick nothing from this first section, 1 thing from this first section, 2 things from this first section, or all R things from this first section, anything from 0 to R. So what's my K? My K is number of objects to pick in this kind of first section. And so this, I'm going to call this like my first section, this second section. So what are my cases? Well, my cases are, I could pick nothing from the first section. I could pick 1 thing, 2 thing, 3 things, all the way up to all R things from the first section. So those are my cases. So for fixed K, how many ways are there? So if I fix K, I have to pick K things from the first section. Well, there are M choose K ways to pick from the first section times N choose R minus K ways to pick from the second section. as I think, as I explained, with this specific example, k equals 2. And so for fixed k, there are this many ways to pick a subset of size r. There are m choose k ways to pick k things in the first section, n choose r minus k ways to pick things in the second section, and I just take those k and r minus k objects, combine them together to get my subset of size r. And well, this is the number of ways for fixed k. So then the total number of ways is how many ways for k equals 0, how many ways for k equals 1, how many ways for k equals 2. So total will be, I'm going to sum k equals 0, k equals 1, k equals 2, all the way to r. And for fixed k, how many ways? M choose k, n choose r minus k. And so that is why it solves this counting problem. Number of subsets of size r in a set of size n plus n. All right. For the sake of time, I want to move on to talking mostly about probability. I'm going to give a very brief introduction to the idea of probability, and then just launch into the more complicated things of like conditional probability, Bayes rule, and related topics. The way I like to think, so there are a few ways. I think there are essentially two main ways that we are thinking about probability in this class. One is the notion of events, and one is the notion of random variables. And I want to first give the notion of events. I'm not going to do this in any kind of rigorous manner, but I just want to do this in a way so that you are more likely to get the correct answer, and a way of intuitively kind of thinking about this. And so what we can think about probability is we can think about that there's like a box. You can think about this box, and this box contains all possible outcomes. And this box, we call it the sample space. Contains many, many possible outcomes. An event is simply a subset of the sample space. So this I could call an event A, just a kind of piece of the pie here. And the probability of A is simply just the probability of any outcome in A happening. I could have a second event like this, and I can call this B. So I have A here, B here. And the key kind of thought that I want to have here is, what's probability of A, of B given A? The way you can think about this sort of is like, what's the probability of A? Probability of A is like, what's the proportion of the whole sample space is covered by this A event? This is a very intuitive sense and not rigorous in any way, but I think it's helpful to think about it in this format, which is, what's the probability of A? Well, the probability of A is like, what portion of this whole sample space is taken up by this A event? And what's the probability of B? Is the proportion of space is taken up by this B event. Well, what's the probability of B given A? B given A is, I know that A happens. Therefore, I know I'm in here. If I know I'm in here, what's the probability of B? Therefore, this is no longer the proportion of B over the whole sample space. This is the proportion of B inside of A. So here's the line for B. This is how much of, if I know A happened, I know I'm inside this shaded region. The probability of B given A is, what's the proportion of B inside the section A. And so it would be this area divided by this area. And so that's the reason why this formula is probability of A and B divided by probability of A. I want to jump directly now into talking about Bayes' rule and so I have an example here about conditional probability, and I hope that this example will not only show you how to use Bayes' rule, but also give you a sense of where this rule comes from, so that it's like easier for you to remember. Let's say that I have two coins. I have one coin, I have coin 1, where the probability of heads is 2/3, and therefore probability of tails is 1/3. And I have coin 2, the probability of heads is 1/5. We have a prior on, and so the game that I want you to imagine that's going on is that you're handed one of these two coins at random. And you want to sort of infer, you want to figure out which coin you have. Now, what are the priors? A prior is simply, how likely do you think you're being handed each of the two coins? So I'm going to say this coin 1, I'm going to call this CH. Coin 2, I'm going to call this CT. And the reason I'm calling it CH is because coin 1 is biased towards heads. Coin 2 is biased towards tails. And so let's say initially you think, it's equally likely I'm going to get, either one. So that means the probability of getting CH is a half. Probability of getting CT is also a half. And so what are these probabilities actually? These probabilities are now conditional probabilities. This is not the probability of heads. The probability of heads is not actually 2/3, because you might get CH or you might get CT. But what you do know is the probability of heads given CH. If you know that you got CH, probability of heads is 2/3. If you know you got CT, let me write this bigger. If you know you got CT, the probability is 1/5. The first question I want, so what happens now in this game is that you're handed one of these two coins and you flip it and you see what the result is. And let's say you came up with heads. Let's say you got handed one of these two coins and you flip it and you came up with heads. The prior indicates you think it's equally likely I'm going to get the heads biased one or the tails biased one. And these tell you the probabilities of each coin flipping heads. Now that you see, once you flip your coin and you see that it's heads, what's the probability that you actually got the heads biased one? What's the probability that you actually got your tails biased one? So in other words, once you see the result heads, you now want to update kind of your beliefs. You want to say, well, maybe it's not quite equally likely that I'm going to get heads, like the heads biased one and the tails biased one equally likely. I flipped heads, maybe it's more likely that I'm going to get, it's actually more likely that I'm going to get the heads one rather than the tails one. And so this key idea is, the idea here is the priors are saying, what's the probability I'm going to get one or the other? So that means that we have to now compute probability of CH given H. this here, it may not be obvious how to calculate this at first, because the only things that I'm given are H given CH, H given CT, and now I have to reverse the conditioning. I have a probability that I get the heads bias one, given that I saw a heads. How do I calculate this? The way I like to think about this is I like to think about it in terms of, so first I'm going to write this out in terms of the definition, and then I'm going to give you sort of the intuitive way of thinking about it. This is probability of you get the heads bias point and you flip heads divided by probability that you get heads. Now, what's the probability that you get heads? The probability that you get heads is not 2/3. The probability that you get heads is not 1/5. Because there is some probability of you getting the first one, and then it would be 2/3. And there's some probability of you getting the heads bias one, and then the probability would be 2/3. There's some probability of you getting the tails bias one, and then it would be 1/5. So the overall probability of flipping a heads is not 2/3, it's not 1/5, but it's some weighted average of 2/3 and 1/5, because there's some probability you might get the heads bias one and then get probability 2/3. There's some probability you might get the tails bias one and get 1/5. And so even this calculation of probability of heads may not seem, too straightforward. The way I like to try to do this is to draw a tree. And the way I draw the tree is I look at the probabilities that I have. So the first thing is you really want to write out these in terms of these kind of events. And then I'm going to look at these probabilities that I have. So write out your probabilities in terms of the events and look at these probabilities and then make this tree. What is this tree? My first layer will go with the ones that don't have any kind of conditioning. What probabilities do I have that have no conditioning? CH, CT. And what's the probability of traveling along this path? 1/2. Probability of traveling along this path? 1/2. If I'm sitting at CT, there are two possibilities. I could get a head or a tail. And what's the probability that if I'm sitting at CH, what's the probability I get H? 2/3. Given I'm at CH, what's the probability given I have the heads bias coin, what's the probability I get heads? 2/3. This has to be 1/3. And similarly, given I'm at CT, the probability of heads 1/5, 4/5. Now, if I want to calculate CH and H, that means that I had to get the heads bias point and I had to flip heads. And so the probability of getting CH and H is 1/2 half the time I get CH. And out of that half proportion, 2/3 of the time I get a heads. So therefore, half the time I get CH, and out of that half of the time, 2/3 of the time I get heads. Therefore, this is 1/3. So 1/3 here, this is probability of CH and H. Similarly, I can calculate all the other probabilities. This is 1/2 times 1/3. So this would be 1/6. This is 1/2 and 1/5. This is probability of CT and H. And then this is 1/2 times 4/5. This would be 2/5 probability of CT and T. Now, what's the probability that I get heads? Well, the probability that I get heads is that I traveled along this path, or I traveled along this path. And so therefore, the probability of heads is equal to the probability of traveling on this path plus the probability of traveling on this path. Well, what's the first path? That's the probability of CH times the probability of heads given CH, or plus traveling on CT times probability of heads given CT. So in other words, this would be this one 1/3 plus 1/10. And this here, I just used the law of total probability. Now, what's probability CH and H? Well, it's just this path here, 1/3. So how do I calculate this? Well, the numerator is just this one, 1/3. And the denominator is probability of heads, which I calculated here, 1/3, 1/3 plus 1/10. I can calculate this out. Let me see if I can do it quickly. So here, this is 13 over 30. So it should be 10 over 13. In a similar manner, I can also calculate what's the probability of CT given H. And this should be 3 over 13. You can run through the whole Bayes rule again, and you can figure it. You can figure out it will be 3 over 13. But the other way I can think about this is, if I see a heads and there's a 10 over 13 probability that I got the heads bias coin, then there must be, if I saw heads, there must be a 3 over 13 probability that I saw the tails bias coin. What this essentially does is, this is essentially a, the terminology for this is the posterior probabilities, or in other words, we kind of updated what our priors are. Initially, I thought I was half chance heads bias, half chance tails bias. But now that I saw a heads, I now think there's a 10 over 13 chance I'm going to get heads bias, 3 over 13 chance I'm going to get tails bias. So now that I saw a heads, what's my next probability of getting a head? How would I calculate now that I saw a head, what's the probability that if I flip it again, I would get another heads? And the way just to think about this is the probabilities that are updating are the probabilities of my belief. What's the probability that how likely do I think I got a heads bias coin, and how likely do I think I got a tails bias coin? Initially, it was half-half, but I flipped it once I saw a head. So now I'm saying, you know what, it's probably 10 over 13 chance I have a heads bias coin, 3 over 13 chance I have a tails bias coin. Now, what's the probability of getting a heads? Essentially the same thing as the calculation we did here. However, this calculation here does the probabilities here are the probabilities I wrote here are the ones that were for my previous belief. Now that my belief has been updated, I now have a new tree. I now have a new probability tree with my updated belief. So this causes a new probability tree. And what does this probability tree look like? Well, it's the same as this one, just with updated belief probabilities. What's the probability of CH? 10 over 13. What's the probability of CT? 3 over 13. And then if I get CT, then the same HT, HT. 2/3, 1/3, 1/5. Now that I've seen a heads, what's my new probability? New P of H. My new P of H is calculated with this new tree. And if I see a heads again, what's my new belief? My new belief is now calculated with this tree. So the way to do these problems is, I'm going to start with an initial prior. When I have my initial prior, I can calculate what's the probability of getting heads. I can calculate what's the probability that if I see heads, I'm going to think it's the heads bias one. And I can do all this calculation with my initial prior. Once I do this calculation, now I have having seen a heads, I now update my belief to change the likelihood that I think I got one or the other to the new, CH given H, CT given H. And I get a new tree here. Now I can repeat this process. What's the probability of getting heads here? So that's saying, what's the probability that, so what this is saying, this new tree is saying is, I got one of the coins at random. I flipped the coin and I saw heads. Given that I've now seen a heads, what's the probability I'll see another heads? That can be calculated by doing probability of heads on this new tree. if I see two heads. So like now that I've seen a heads, and what if I got the coin, I saw heads, what's the probability of seeing heads? I can calculate that with this new tree. What if I flip it again and I see another heads? Now what's my new probabilities? I do the same thing, Bayes rule, but with this new tree. So effectively, this is an iterative process in which using the data that I collect, I change my likelihood belief of how likely I got this one and how likely I got this one. And ideally, as you flip more and more, your belief tends more towards one side than the other. All right, I want to. So just in summary, this whole process is summarized in these two calculations that we did right here. Once I do these two calculations, when I go into the next round, all I do is I just change my prior belief probabilities to these new ones. What's the probability of CH, probability of CT that I calculated here, and then just redo the whole calculation again. All right. So this concludes the section that I want to talk about conditional probability. And now I want to give you an example of. I now want to give you like the other way of thinking about probability that we have in this course, which is about random variables. And so I'm going to move the board up, but I think people here can still see it. I know people on Zoom can't, but it's going to be essentially sort of a totally different way of thinking about probability. But it's an important one that's going to show up a lot in tests. So I'm going to switch the boards and we're going to talk about random variables. Random variable. The way I like to think about a random variable is that a random variable is a signal. A random variable is effectively a signal telling you some information about a random experiment. The visualization I like to have in my head is that we have this box here. Inside this box, a random experiment is being conducted. They could be rolling a die, they could be like flipping a coin. You aren't allowed to see what is going on inside. However, there is a screen, and the screen displays a number that gives you some information about the outcomes of the random experiment that are going on inside. I'm going to give it an example. Let's say the random experiment going on inside is that they're rolling a die. What could pop up on the screen is the number that's being rolled inside. So if you see a 3, you know that inside they rolled a 3. See a 6, you know they rolled a 6. The way to specify a random variable, if I give a random variable, often you see a random variable in terms like an X kind of thing. All that X is the X is referring to a screen. And how do I specify the information? How do I specify a random variable? The way to specify a random variable is to say, well, what values can it take on with what probability? That effectively gives you all the information that you can get about the behavior of this screen. What values can the screen show, and with what probability is that screen going to show that value? In the case of rolling a die, the values are 1, 2, 3, 4, 5, and 6, each with probability 1/6. However, we could have, when I define for you a random variable or explain that the intuition behind what a random variable is, I never specified that this screen had to give you sort of all the information. It just had to give you some information about what's going on inside. So another possible random variable is we could have another screen here, let's say the screen Y. And what the screen Y says is it tells you whether the value that was rolled was even or odd. So let's say even, 0, 1, odd. And what are the probabilities? Probability 1/2 here, probability 1/2 here. The specification of a random variable, by specifying all the values that it can take on as well as corresponding probabilities, this is called a distribution. In this case, we have two discrete random variables, and this effectively gives you the probability mass function. To draw this out for x, 1, 2, 3, 4, 5, 6, and they're all kind of like uniform like that at 1/6. I want to now just give a little bit on what happens if you have something like x squared. I know this notation of x squared may be confusing. Normally, when you have an x squared, it's just that you have a number x and you square it. But now I have a random variable x. What's x squared? And this is where I think it's helpful to think about this kind of screen analogy. What's x squared? X squared is a screen. We have another screen here. This is like a 2-story house now. So x squared is another screen. And what this screen shows is whatever my screen x shows, my x squared screen is going to show the number on x squared. So whatever my x screen shows, if this shows 3, my x squared screen is going to show 9. X squared screen is whatever my x screen shows, my x squared screen is just going to show the square of it. And so to define now what the distribution of x squared is, well, what are the possible values that x squared screen to show? Well, it only can show the square of what comes up on the x screen. Therefore, I can only show 1, 4, 9, 16, 25, and 36. And with what probability? With probability 1/6. Right? Because the x screen has probability 1/6 of showing 5. The x squared screen has probability 1/6 of showing 25. I want to caution you of one thing, which is it is not necessarily always the case where I can just like get out the new distribution just by applying the right function. If I were given, say, like a new random variable z, which had -1, 0, 1, with probability 1/3, 1/3, 1/3, you could not say like z squared has like 1 probably 1/3, 0 probably 1/3, 1 probably 1/3. Because here these two kind of combine to be the same thing. In this case, 0 would still be 1/3, but 1 would be this and this. So therefore, the 1 would have 2/3 of probability of showing up. I want to now proceed to doing an example, which will cover many of the topics related to random variables. let's say that we have a grid. And at every point on the grid, so let's say we start here and we have a cat named Zima. This actually has a history. When I first TA'd this class, so this is spring 2021, there was a head TA and she had a cat named Zima, and Zima became the class mascot. And so I wrote this problem about Zima, and it's kind of stuck ever since. But I think most of you, or almost all of you, probably have no recollection of Zima. Zima, I think, has disappeared from this course, actually, except for now. Zima is sitting at the origin. And with probability P, Zima is going to go upwards or rightwards at every juncture here. And with probability P, Zima is going to go up. With probability 1 minus P, Zima is going to go to the right. And I'm going to define this random variable x to be Zima's x position, a random variable y to be Zima's y position. And I'm going to calculate for you various properties of these two random variables. Oh, and one thing is Zima takes n steps. So x and y are after n steps. So it's like 1, 2, 3, 4, 5, 6, 7 or something like that. A helpful way to split this up is Zima's x position is equal to x1 plus x2 all the way up to xn. And what are these random variables? Oh, and one extra thing is that all the moves are independent. So which way? So it's always p probability upwards, 1 minus p probability to the right. X, here I can write this as the sum of n random variables, x1 to xn. And x1 to xn describe the change in Zima's x position at time 1, time 2, up to time n. So or step 1, step 2, up to step n. So xi, so at step I, Zima's x position can change by 1 or 0. It would change by 1 with probability 1 minus p. It would change by 0 with probability p. What you may begin to notice is that x here is a binomial random variable. Xi is Bernoulli. But what I'm going to do is I'm going to do the calculations out for you, not by just looking at a table, but like sort of deriving them out to you. And I strongly recommend that you also know how to do this derivation. On the exam, if you recognize a random variable as being binomial or Bernoulli or geometric or something like that, you can automatically, it will be helpful for you to have the formulas memorized so that you can cite them immediately. But in case you forget, or in case you stumble or things like that, I think it's helpful also to know this derivation because it combines a lot of the important concepts in terms of random variables. I want to first calculate for you what is the expected value of x. Well, what's x? X is the sum of a bunch of random variables. I equals 1 to n. Linearity of expectation. Sum I equals 1 to n. Expected value of xi. What's the expected value of xi? To calculate expected value of xi, I simply take each of these products and I sum them up. So it's 1 times 1 minus p plus 0 times p. So this is 1 minus p. And so this I get is the sum from I equals 1 to n of 1 minus p. And therefore, this is n times 1 minus p. You realize that this is exactly the expected value for a Bernoulli random variable parameter 1 minus p. I can do a similar derivation for y, and I can get expected value of y. You would get n times p with essentially exactly the same calculation. Now I want to calculate the variance of x. What's the variance of x? Well, the variance of x is the expected value of x minus the expected value of x squared. the intuitive thought about this formula is the variance of x is x minus expected value of x is like the distance of x from its mean. Why do I square it? Is because x minus e of x would be positive if are greater than the mean, negative if are less than the mean. So I do the squaring to just kind of capture like the square distance from the mean. That way that I'm always adding up positive distance, whether I'm less than or greater than. Variance is just the expected, the average square distance from the mean. If I work this out, which I'm not going to work this out completely, but this is expected value of x squared minus the expected value of x all squared. What I'm going to calculate for you here first is the variance of xi for one step. This is the expected value of xi squared minus the expected value of xi quantity squared. Expected value of xi, so I just need to calculate this because here I've already calculated it up here. Expected value of xi squared. What's xi squared? What's the distribution? Remember, it's just whatever xi is, whatever the xi screen shows, my xi squared screen is just going to show the square of it. So my xi screen showed a 1, my xi squared screen will also show a 1. If my xi screen showed a 0, my xi squared screen will also show a 0. Because I'm just taking the square of what shows up on this screen. And with what probabilities? Well, 1 has a 1 minus p probability of showing up, and 0 has a p probability of showing up. And so the expected value of xi squared is simply 1 minus p, and then minus this squared. What's this? Well, this is also 1 minus p squared. And so here I can essentially factor this out. 1 minus p times 1 minus 1 plus p. And this I will get p times 1 minus p. Now to calculate variance of x. A key thing to remember is that when you have independent random variables, the variances will add. And therefore, since I have n random variables, n independent random variables, the variances will add. So I get p times 1 minus p, p times 1 minus p, p times 1 minus p. So in total, I have n times p times 1 minus p. Good. I want to now pull now in the case of, say, now there are two inequalities which I want to go over. One here is Markov's inequality. And to demonstrate this, I'm going to prove a statement, which is the probability that the x position is greater than or equal to alpha, plus the probability that your y position is greater than or equal to alpha, is less than or equal to n, the number of steps divided by alpha. So I'm going to prove this. What's Markov's inequality? Markov's inequality says probability that my random variable x is greater than or equal to alpha is less than or equal to expected value of x all divided by alpha. Oh, and a kind of technical point is that x has to only take on non-negative values. So here, what's the probability that x is greater than or equal to alpha? Well, this part is less than or equal to expected value of x over alpha. What's expected value of x? Well, we calculate that as n times 1 minus p divided by alpha. This is less than or equal to expected value of y, n times p over alpha. So I sum these up. This is n over alpha, and so therefore I've proven this is less than or equals to n over alpha. A probably slightly more confusing inequality that would be Chebyshev's inequality. And this inequality states that this. I think it's greater than or equal to alpha. Intuitively, what this means is, what does this say? This is saying, what's the probability that my random variable x is alpha far away from its mean? So if I had a distribution kind of thing, and let's say here was its mean, what's the probability that I'm alpha far away from the mean? So what's the probability that like my x is like all the way over here or all the way over here? And what this is saying is that the probability that all the way over here, all the way over here is less than or equal to the variance of x divided by alpha squared. So as an example for applying this inequality, I want to say what's like after n steps, let's say Zima takes n steps. Can I find, so after Zima takes n steps, you can imagine Zima goes like up, right, or like, something like this. After n steps, can I find like an interval where I know with 99% probability Zima's x position is within this interval? Can I find like a 99% kind of like confidence interval? I know 99% sure Zima is within this interval after n steps. Well, then what do I need? Well, what this is saying is that if I'm alpha far away, so let's say here's where the mean is. Here I have alpha far away, here I'm alpha far away. What I want is this quantity, which is the probability outside the interval, to be 0.01. I want variance of x over alpha squared to equal to 0.01. And so in other words, I need alpha squared to equal to 100 times the variance of x. In other words, this is 100 times n times p times 1 minus p. And so therefore, alpha has to be 10 square root np1 minus p. And so if here's my mean, my alpha, if my alpha is this value, I know with 99% probability, Zima is within this interval. So what's the interval? Well, the interval is just expected value of x kind of plus or minus this specific value of alpha here. And now also just give a quick explanation of covariance. So let's say we're talking, so the covariance of two random variables, and the random variables I'm going to use are x1 and y1. The definition of covariance is that it's the expected value of x1 minus expected value x1, y1 minus expected value y1. This is the definition. What's the intuition behind this definition? If my covariance is positive, I'd like to think about it this way. This is the average product of x1 minus expected value x1, y1 minus expected value y1. So what this is saying is x1 minus expected value x1 is kind of like, am I bigger than my mean or less than my mean? Y is, am I bigger than my y mean or less than my y mean? The intuition I like to think about for this covariance is that if the covariance is positive, that means on average, maybe this diagram is not going to help so much, but on average, if my covariance is positive, it means that this and this tend to have the same sign. So this and this, tend to have the same sign. What does that mean if they have the same sign? If they tend, on average, they tend to have the same sign. Means that on average, if x is bigger than its mean, y is probably also bigger than its mean. And if x is less than its mean, y is probably also less than its mean. That means x and y are in fact positively correlated. If x gets bigger, y tends to also get bigger as well. This is positively correlated. If the covariance is less than 0, the opposite effect is true. As x tends to get bigger than its mean, y tends to drop below its mean. And as x goes below its mean, y tends to get bigger than its mean. So this means that these two terms tend to have different signs. Negatively correlated. In other words, it's like if you know that like x is going to be bigger than its mean, and it's positively correlated, that means you're going to be pretty sure y is also going to be bigger than its mean. Conversely, if it's negatively correlated, if you know x is going to be bigger than its mean, you're pretty sure that y is going to be less than its mean. I'm going to expand this part out a little bit. This here, if I do the calculations, it will be expected value of x1, y1 minus expected value of x1, expected value of y1. And in order to do this calculation, I'm going to do this one quickly for you for x1 and y1. What's the random variable x1, y1? x1, y1 is a screen that's going to output what value? It's going to output the value that x1 screen outputs, the y1 screen outputs, multiplied together. That's what's coming out on my x1, y1 screen. So my x1 can output 1 or 0. My y1 can output 1 or 0. And so therefore, my x1, y1 screen can also output either a 1 or a 0. When is it going to output a 1? It's only going to output a 1 if my x1 screen outputs 1, my y1 screen outputs 1. And it's going to output 0 if my otherwise, if any other case happens. What probability? With what probability is x1, y1 going to output 1? That means my x1 screen has to output 1. My y1 screen also has to output 1. That means that Zima had to travel rightward on the first step and upward on the first step. Probably 0. And therefore, it's going to output this with probability 1. What's the expected value of this? 1 times 0 plus 0 times 1, 0. Now, we already calculated expected value of x1 and expected value of y1. And so therefore, I can calculate the covariance. x1, y1. This is 0 minus expected value of x1, which is should be 1 minus p. Expected value of y1, which is p, and so I get negative p times 1 minus p. Why does this make sense? This means the covariance has to be negative because p and 1 minus p are both positive. Why does this make sense? If I know that Zima went upwards, I know that Zima didn't go to the right. Therefore, if I know x1 increased, I know that y1 did not. And so that's why the covariance is less than 0, because we know that these two tend to have different signs. If x1 increases above its mean, that means Zima took the upward path. Zima took the rightward path. We know that Zima didn't take the upward path, and so we know that y1 probably decreased below its mean. It's also another notion of correlation, but it's really just the covariance divided by some normalizing factor. And so I encourage, and I believe it's divided by like the standard deviation. And so since we've already calculated the variance, we've essentially calculated all the pieces that you would need. So the one last thing that I want to, so I know it's 5 p.m. There's one last thing I want to cover, which is how to do these induction proofs with probability. And so if you need to leave, you're welcome to leave, but I'll cover it so that it will be in the video. And so if you ever need to watch it, you're like, you can always reference back to it. This one last thing that I want to do is these kind of inductive proofs involving probability. For this, I'm going to give this example. Let's say we have a number line 0 up to 10, 0, 1, 2, 3, so on up to 10. And let's say you are standing right here on spot number 3. There's a half chance that you will go to the left and half chance that you will go to the right at every point here. And what we want to calculate now, we want to calculate the probability. What happens is that once you hit 0, you stay here. Or if you hit 10, you stay here. And here, what I'm going to ask is, what's the probability that you get to 10? In order to solve this problem, so I'm going to now calculate, I want to calculate what's the probability that you end up at 10. So let's say here 10, like there's like something good here. 0 is bad. And what's the probability that you get to 10? For this, I'm going to prove the following statement. Let P of I, the P sub I, be the probability. So following this kind of half-half procedure, what's the probability that you get to I plus 1 while standing at I? In other words, instead of thinking about you being bound from 0 to 10, let's say you're standing at 3. P of I is, what's the probability that you get to 4? So like one way you get to 4 is you can hop here, or you can go like this, or you can go like back and then back to 4. Let P of I be the probability that you get to 1 to the right while you're standing at I. What's probably you get to I plus 1 when you're standing at I? And sort of the thing that like prevents you from this always happening is that you could possibly hop backwards and hit the 0. And so the first step is, let's write a recurrence for this. The recurrence for this is, well, P of I, what could possibly happen? One choice is that, so half the time I just go to the right by 1. And if I go to the right by 1, I automatically succeed. The other half of the time, I go to the left by 1. And then what do I have to do? Well, first I have to get back to, so if I'm standing at 3, if I went to the left, I have to get back to 3 and then get back to 4. In other words, if I went back by 1, the probability that I get to, if I'm standing at 3 and if I went back to 2, the probability that I get to 4 is the probability I can go from 2 to 3. That's P of I minus 1. Times the probability that I go from 3 to 4, P of I. And now I can solve for P of I. I can bring this to this side, 1 minus 1/2 P of I minus 1 equals to 1/2. And I'm going to spare you the algebra and P sub I equals to 1 over 2 minus Pi minus 1. That gets me my recurrence.
A question.
Yeah.
Can we simply use a Markov chain here?
Yes, but I want to use this to demonstrate the technique for the problems on the exam. So I mean, there are many ways to solve this problem, and if I might want to show you a very fast way to solve it, which does not require recurrence at all. But now what I'm going to prove is I want to prove that P of I is equal to I over I plus 1. My base case, I equals 0. Well, P of I is what's the probability I get to 1 if I'm standing at 0? Well, I'm not going to get to 1 because if I'm standing at 0, I'm just going to get stuck there. So the chance that I'm going to get to 1 is 0, which is equal to 0 over 0 plus 1. Inductive hypothesis, P of I is equal to, and this statement, we can call this our big P of I, and we're inducting on I. Inductive hypothesis, P of I is equal to I over I plus 1. What's P of I plus 1? Well, I can just use my recurrence, 1 over 2 minus P of I. Now I'm going to use inductive hypothesis, 1 over 2 minus, what's P of I over I plus 1. And to spare you the algebra here, this would be 2I plus 2 minus I over I plus 1, and this becomes I plus 1 over I plus 2 as desired. Going back to this original problem, what's the probability that I get to 10? The probability that I get to 10 is if I were standing on 3, what's the chance that I get to 10? Well, it's simply, what's the chance that when I'm standing at 3, what's the chance that I get to 4? That's P3. So my original problem, what's the probability that I get to 10? Well, that's P3, because it's from 3, what's the chance I hop to 4, times P4, what's the chance that from 3 I can get to 4? What's the chance from 4 I can get to 5? That's P4. What's the chance I can go from 5 to 6, 6 to 7, all the way up to P9, 9 to 10? This is 3 using the thing that we just proved, 3/4 times 4/5 times 5/6, all the way up to 9 over 10. Simplify all this, and I get 3/10. However, there is another way. So I did all of this work to demonstrate to you the technique of doing the inductive proof. But here's another way I can solve that it's 3 over 10. Let me define a bunch of random variables. Let me define, say, x0 to be your position right at the start. X1 to be your position after you take 1 step, all the way up to as many as I need. X0 is I've taken 0 steps, what's my position? X1 is I've taken 1 step, what's my position? X2 is I've taken 2 steps, what's my position? And you can see that like X2 has a distribution, ranging from 1 to 5, because I could have taken 2 right steps, 2 left steps, or any combination in between. And what I'm going to say is I'm going to define another random variable ti, and ti tells me the change in my position at step I. And so what's ti? Well, it's going to be +1 with probability 1/2, -1 with probability 1/2. Because with probability 1/2, I could go up 1 or back 1. And so that's why x1 is simply equal to x0 plus t1. X2 is equal to x0 plus t1 plus t2. And so on down all the way until like you end. What's the expected value of x0? Well, there's only one place I could be right before I take any steps. Where can I be? It has to be 3. Because I'm with probability 1, I'm standing at position 3. How about expected value of x1? Well, by linearity of expectation, it's expected value of x0 plus the expected value of t1. What's the expected value of t1? 1 times a half. So expected value of x0 is 3 plus expected value of t1 half minus a half. 3. In fact, any ti, expected value of ti, is 0. Which means that for all of these random variables, where's my position after I take 0 steps, 1 steps, 2 steps, 3 steps? All of these random variables, expected value of xi is simply the expected value of x0 plus the expected value of a bunch of t's, which are all 0, plus 0. Which means that at the end of this procedure, once you've hit one of the endpoints, what's your expected value? Still 3. Now, if you're at the... So once you finish this game, your expected position is still 3. Which means that when you finish this game, let's say that you finish this game at xf. Let's say xf is that when you finish this game. Expected value of xf is with probability p, you are at 10. And with probability 1 minus p, you are at 0. When you finish this game, there's some probability that you ended up at 10, and the other probability that you end up at 0. The expected value of this, your expected position never changes. So this has to equal to 3. And if I solve this, p is equal to 3/10. The probability that you end up at 10 is 3/10. No need for recurrence or anything like that. So that essentially concludes all of the things that I wanted to cover. Yeah. Okay. Maybe we can talk about it after. Yeah. Yeah. So that essentially concludes all of the things that I wanted to cover for you today. I will probably hold one more office hour next week, but it may not be at the normal time. Other than that, I won't be able to see you at the final because I have a final at exactly the same time. But just want you all to know it's been a pleasure being your TA this semester. I've really enjoyed it. Yeah, so I wish you all the best. Thank you for a great semester. Yeah. Sure.